Okay, so a couple of little extra bits. On page 283, I'd like to just mention three questions. So this is New CGP Pure Book, page 283. I'd like to talk about questions 5, 7 and 10. So question 5 first. We're told about the flight path of a toy aeroplane being modelled by the vector 2m minus n, and we're given the vector m and we're given the vector n. And we're asked to find the distance of the plane's destination. So if it follows that journey, how far away is it from its start point? So we've got m is minus 5 minus 2, 6, n is minus 4, 1, 2. So 2m minus n just means two lots of that minus one lot of that. And it is just as simple as doing the sums. You could try and draw it, but you don't need to. So two lots of minus 5 is minus 10, minus 4, so that's minus 6. Two lots of minus 2 is minus 4, minus 1, and 6, two lots of that is 12, minus 2. So that's the entire journey, and so the length of that journey is just the square root of that squared plus that squared plus that squared. And I'm sure you can work that one out. Okay, I'm assuming you know, I can sort of keep going here and you'll pause it whenever you need to, rather than me having long pauses. Question 7, we did do this last year, but find the unit vector in the direction of the following vectors. So here we've got a vector. The unit vector is a vector that's parallel to this one, but which has a length, a magnitude of 1. So here's how I would do part A. So this is the vector we're given. So I'm going to work out the magnitude of that vector. So it's the square root of that squared plus that squared plus that squared. 16 plus 16, that's 32 plus 49, that's square root of 81, which is 9. And so a vector that's parallel to this one is just one where every number gets multiplied by the same thing. And you can prove that, we don't need to prove that. If you divide each of these numbers by the length, you get a vector with a length of 1. So the unit vector is 4 over 9 minus 4 over 9 minus 7 over 9. So all I've done is taken each of those values and divided by the length. And yeah, check it. Do the square root of that squared plus that squared plus that squared, and you will find you get 1. And then thirdly, question 10. A toy rocket is launched at an angle of 60 degrees to the unit vector in the I direction. Now that, remember, the I direction is a vector of unit length, so length 1 in the x-axis direction. And then here we've got a three-dimensional vector, which is 1i plus aj plus 1k. We know the angle between the unit vector in the I direction and this vector, and we're asked to work out the missing values. So this is very much like finding the angle between two vectors that we did in the previous video. Here's the problem drawn out for you. So this is the unit vector in the I direction. So it's a vector of 1, 0, 0. 1i, no j's, no k's. This is the vector that we're told of the velocity. So that is 1i, aj, and 1k. So what we're going to do is, and it's my diagram, I foolishly made a diagram that looks like it's going to be a right angle triangle. I have no idea whether it's a right angle triangle because this is a three-dimensional line. I don't know what it looks like. So it's not a right angle triangle necessarily. So I'm just going to do what we did in the previous question. I'm going to work out this vector here. So that's minus that plus that. So minus 1 plus 1. Minus a plus nothing, and minus 1 plus nothing. And so I've got 3 lengths, so I can use my old friend, the rearranged cosine rule, to work out the angle, or in this case, I already know the angle, so I'm going to use the normal cosine rule, and I'm just going to plug in the values and work out the length of this one, which will be in terms of a. So the length of this one is the square root of that squared plus that squared plus that squared. I'm going to work out the length of this, which is that squared plus that squared plus that, and I'm going to work out the length of this, which is just the square root of that, so that's just 1, obviously, unit vector, always to the length of 1. And I'm going to either plug that into this, I know what cos 60 is, or I'm going to use the normal cosine rule, and we should be able to work out a. Just be careful, don't forget that this a here is not that a there, is it? So let's make sure we're clear. If that's the angle that we know, then that's big A, that's little a, and these two are B and C, and it doesn't matter which way around they are. Now, I'm going to leave you to solve that one, as I am leaving you to solve 5 and 7, and let me know if you have some problems, and I'll happily go through it with you again. Okay, the last question I'd like to talk about is question 15 on the first mock paper that I shared with you last week. So I don't know if you've had a go at this yet, but I'm going to sort of tell you how I would start it, but I'm still going to leave you to finish it off. So we're given this information about 2 points, OA and OB, so yeah, we've dealt with problems like that. We're then told about 2 other points, C and D, and we're told how to get to C from B and how to get to D from A. And then I see lower down that ABCD is a trapezium. So when they talk about these sorts of shapes, the points are always going to be either clockwise or anti-clockwise. And this is a trapezium, so I know it's either going to look a bit like this maybe, or this, or it could look in a variety of different ways, but I'd note that, and a trapezium, sorry, 1 pair of parallel sides, hasn't it? 4 sides, 1 pair of parallel sides. I note here that BC and AD are not parallel. They're not parallel. I know that because one is not a multiple of the other. So it can't be this, can it? Because in this way I've done it, BC and AD are parallel. Now it doesn't mean it has to look like this, but I'm going to have a punt and guess that it's like that. Okay, so that question there, here's the diagram I drew for it. So I've got my 2 position vectors, OA and OB, and then I know about the journey AD and BC. And like I say, I'm not sure at the moment that these vectors are arranged correctly, but I've got them going in a clockwise direction. Now, I hope the first part is nice and easy. You've got to find the position vector of D, and that just means what's this journey here from O to D, and I can get that by going up that branch and down that branch. So it's plus that and plus that, so I'm going to leave you to work that one out. But we're then told if ABCD is a trapezium, find the value of P. And this is a parallel vector question. So I'm going to work out the vector AB. Okay, now to get from AB, I go backwards down there and forwards up there. So that's minus 3 plus 3, minus 2 minus 1, and minus 7 plus P. I'm also going to work out the vector DC. Now, to do the vector DC, I could go a variety of ways. I think the way I'm going to do it is I'm going to go up there, so that's minus that vector. I'm then going to go along AB, so it's plus that vector, and then along BC, so it's plus that vector. So to get from D to C, I'm going to go this way round. So D to C, that journey is minus 2, then along this vector, so plus 6 plus nothing. It's minus 5 plus that, so that's minus 3, minus 8 plus 6 minus 2, and then it's minus that, so that's 4. Is that right? Yes. Yes, plus 4, and then plus this, so that's minus 7, so plus 4 minus 7 is minus 3 plus P, and then minus 7, so that's going to be minus 10 plus P. Now if this is a trapezium, I know now that these two sides aren't parallel. This isn't a multiple of this. I can also see that neither of these sides are parallel to AB. So these two have got to be parallel. And that means that this has got to be a multiple of this. And I can see that going from 6 to 4, the multiplier is, after divided by the 4, 2/3. Let's check to see if it works for the second value. It does. To go from, sorry, can't see the 2/3. To go from minus 3 to minus 2, you multiply by 2/3. And that means that this multiplied by 2/3 must equal that. And so that's the simple problem they're asking us to solve here. We know that 2/3 of minus 7 plus P must equal minus 10 plus P. And I'm hoping that you can go on and solve that one. Good stuff.